Hello guys, I hope you are well. Thank you so much for joining this video of machine learning tutorial. In this video, I am going to explain the gradient descent algorithm. In the previous video, I explained the regression and we reviewed the points related to it and its applications and related symbols as well as formulas, and said that these symbols are used in both formulas and programs. We said that the output of the learning algorithm is a hypothesis function. I started the explanation from the simplest case, which was a univariate linear regression, and said that later we will reach more complex hypotheses and functions. Also in the previous video we introduced the cost function as a method for a quantitative and numerical evaluation of the hypothesis. We said that this function determines how bad the hypothesis is. Finally, we introduced the errors of the error function, which is the sum of squares error function, as one of the common cost functions. We said that to find the best hypothesis, we have to minimize the cost function in terms of theta 0 and theta 1. We emphasized that the optimization is done according to the parameters which are theta 0 and theta 1. At the end of the previous video, we examined a numerical example in this case. So if we want to have a summary, we are looking for a hypothesis function that is as close as possible to the values of our training set. To find the best hypothesis, we need to find the best parameters. Let's consider another example, but this time we will not consider theta 0 to be 0. When a 3D figure is drawn on a 2D plane, some information is lost. We use a color to solve this problem. That is, we show that a missing dimension with color and use the rainbow color spectrum. We are looking for points that are bluer, places that are closer to the blue side of the color spectrum have a lower value of the cost function. It is also called a contour shape. Contour exercises are closed curves where all points on that curve have a common feature. Here, this common property is the J value. That is, points of the same color have the same J value. From now on, we will not draw the contour curve and we'll use the 2D contour image. So we explain the third dimension, for example, the cost function with color. I have included the code for drawing these shapes through NumPy and Matplotlib libraries in Python files. In these codes, I have drawn the figure in Cartesian coordinates. Grid in Python is called a grid, actually, which is a grid-shaped image. In these codes, I have defined the cost function with the name Z for you. You can try them all. Be sure to watch videos on working with Python in the field of machine learning and practice problems. The purpose here is not to explain the code. I just wanted to say that we won't be drawing a 3D bowl shape here. We'll be dealing with a 2D contour image. We want to get the optimal point of this hypothesis function. For this, we want to use gradient descent algorithm. Suppose we draw a probability line that represents the cost function. Qualitatively, we can understand that the line is not a good hypothesis. but the qualitative concepts are not comprehensible to the computer, and we have to use a cost function to define how bad it is. Okay, we can understand qualitatively that this line is not a good idea, but we want to make the computer understand this too. In the figure on the right, we select the random point. We see that it is not the best point. We draw another hypothesis, and we have shown the point representing the values of theta 0 and theta 1 in the figure. You can see that this hypothesis is better than the previous one, but not the best. In the next attempt, we reach a point that is sufficiently better. You can see these attempts here. Okay. We can do this manually, but we need to write an algorithm for the computer. The algorithm we want to use for this is gradient descent algorithm. With the help of this algorithm, we want to find the best point. The best point means the best theta 0 and theta 1. After finding the right parameters and hypotheses, and now we have to enter the testing phase. We test the new data with this hypothesis function to check its performance. This algorithm is very simple. First, we choose a random point, that is, we give random values to theta 0 and theta 1. We start with a random starting point. Now we want to change the value of the parameters so that we move towards the center at the bottom of the bowl shape that had the lowest j. We call each of the blue minimum points a local optimum because they are better than their neighbors. Depending on whether the problem is minimization or maximization, the definition of optimality will be different. Optimality will be different. The definition of optimality will be different. The point that is better than all the available points is called the global optimum. In the first step, this algorithm chooses theta 0 and theta 1 completely randomly. Now we try to change the parameters a little so that the value of the function decreases. We try to see in which direction the value of the function decreases by taking a step, and we take that step in the end. Let's say you're a mountaineer with an altimeter, and the fog is so thick that you can only see a step around you. You are looking for the lowest possible altitude. Take one step in each direction and measure the height. You choose the direction to move that will have the most height loss. We repeat the same thing over and over until we reach a point where there is no drop in height in any direction you move. This point is called the local optimum. Now we want to do the same with the algorithm. Here in this figure, we have 3 local optima, and we have found the best chance. This is purely random because the starting point is chosen randomly. We do not necessarily always reach the global optimum. Suppose you put a ball on top of a mountain. How will it move? We are looking for the same moves. We want to define these algorithms in mathematical terms. You can see the whole gradient descent algorithm inside the loop and formally. At first, we have chosen a random point and we change it a little to reach the optimal point. This is where I say that a differential and linear algebra are needed to understand the concepts of machine learning. In the real world, the number of dimensions, maybe hundreds of millions, in these cases, computer algorithms are needed. We review some mathematical concepts. If you don't understand, please see more courses on mathematics and linear algebra to understand the concepts. We define a vector theta containing parameters theta from theta 0 and to theta n. In this way, our task becomes easier. In our example, there are two variables. In cases where there are several parameters, defining such a vector helps greatly in simplification. In linear algebra, usually when we say vector, we mean column vector. Transpose a column vector, which is always a row vector. We denote the vector transduction by this T. I want to show you the T, which is corresponding with the transpose. Let me introduce you to the T. Okay, I couldn't find that here, unfortunately. There is not a transpose here, but a capital T can represent the transpose of a vector. When you have a column vector, so transpose of that vector will be a row vector actually. Okay. At each point, we seek to move in the direction where we have the greatest reduction. In mathematics, this concept is defined and it is called a gradient. That is, the gradient of a function is the direction in which the function increases the most. A gradient in mathematics is represented by an inverted triangle. We are looking for the direction where the function is decreasing the most. So we are looking for the opposite direction of the gradient. To get the reciprocal of a vector, we must multiply that vector by a -1. Here we have a binary vector because the number of parameters is 2. The first component of this vector is the partial differential of the j function with respect to the first parameter, which is theta 0. You can see this here, okay? The second component becomes the partial difference of the differential of the j function with respect to the second component, which is theta 1. You can see them here. So these can be calculated mathematically inside the computer. So we found the direction, we are taking a step in this direction. In vector algebra, if we add this vector theta with the negative of the gradient vector, we have reached this goal. In this way, we have reached a new point and we must repeat this work constantly. We also define the size of this step with the alpha parameter. This alpha parameter. This alpha is different from the thetas. We call alpha hyperparameter. Hyperparameter alpha is a very important parameter. In this lesson, apart from theta, we call any other parameter as hyperparameter. We choose the alpha as a step size for now. Alpha in this formula is a number, and we call it the learning rate. Its other name is step size. Now we want to write this equation in another way. We can make this equation simpler. We can say the new theta 0 is equal to the previous theta 0 minus alpha times the differential of the cost function with respect to theta 0, which we have written it here. Similarly, in the case of theta 1, it can be said that the new theta 1 is equal to the previous theta 1 minus alpha multiplied by the differential of the cost function compared to the previous theta in respect to the previous theta 1. Now we have only two parameters here. As the number of parameters increases, it becomes difficult to define the equation in this way, so it is better to express the general formula with j like this. We can see the blue box here, that the new theta j is equal to the previous theta j minus alpha multiplied in the partial differential of the cost function with respect to the same parameter theta j. This is actually what we wrote in the algorithm. We said that in gradient descent algorithm, we select a random pointer and update the parameter values in each iteration. How long until the algorithm converges? In mathematics, optimal points are points where the differential is equal to 0. Where the differential is 0, the gradient is 0. And when the gradient becomes 0, the amount of theta will not change. And in other words, the algorithm will converge. So let's update the points in order. Updates must be done simultaneously. That's why we have to do vector calculations. If we update theta 0 first, the next time we take the differential, we have obtained this partial differential at a different point, and this makes the algorithm not change well. Intuitively, we check the algorithm. Suppose we choose a random point. The slope of a point in the function means that the slope of the tangent line to the curve of the function at that point. Intuitively, we knew that we should move to the left in this figure. The slope of this line is positive at this point. Alpha, which is also positive, so in fact we reduce a value in this formula. So considering the formula, we must move to the left. You can see that the algorithm and the formula work correctly. If the initial random point is on the left side of the optimal point, it will not make a difference and the algorithm will still work optimally. Now, if this learning rate is too large, we may jump from the optimal point. We call this state overshooting. This is overshooting. Now, if this alpha is too small, the number of iterations will increase and the convergence will slow down. In fact, whether alpha is too large or too small, the convergence is still slow here when the learning rate is too small. As you can see, the second step is smaller than the first step because the slope at the second point was less than the slope at the first point. The concept of jumping over the optimal point is clear in the figure. Here we have outlined some steps just to understand the issue. In real examples, these jumps may occur millions of times. If alpha is too large, the algorithm may even diverge. That is, you can see that the value of the cost function keeps getting bigger and bigger. Now let's see how this algorithm can be used to solve regression problems. We said that in the formula in the iteration loop, we put j as the regression cost function, which was the error, actually the sum of squares error function. Let's calculate the differentials manually once, and for all in this formula, we need to calculate partial differential with respect to theta 0 and theta 1. When we want to calculate the partial differential with respect to one parameter, the differential with respect to other parameters becomes 0 because those parameters are considered fixed. In this relationship, consider j as 0 to calculate theta j as 0 to calculate the partial differential with respect to theta 0. Consider, since we have just two j's here, j is equal to 0 and j can be equal to 1, can consider j is equal to 0 here in this line. In the second line, actually, consider j is equal to 0 to calculate the partial differential with respect to theta 0. We know that sigma in mathematics means a sum. In differential mathematics, the sum of several terms is equal to the sum of the differentials of the terms. We do the same here. Now we again consider j as a 1 in the last line here, you can see, and consider the partial differential with respect to theta 1. If you are familiar with mathematical concepts, you will understand the general concept by reading the slides. Of course, to work in the field of machine learning, there is no need to perform these mathematical operations manually, and these calculations are all available as ready-made codes in predefined libraries. But I wanted to mention these concepts here for your better understanding. So in fact, this becomes the gradient descent algorithm for solving linear regression problems. If the concepts seem complicated to you, don't worry. After solving various problems and exercises, at the end of this training course, you will completely master the concepts. The last point is that in this video we examined the two forms. One is related to the gradient reduction algorithm that will definitely reach the optimal point, but this point may not be the global optimal point, and may be the local optimal point. The error, the sum of square error function will definitely bring us to the global optimal point by implementing gradient descent, because this function is convex. You can see that. Another type of functions are concave functions. In the discussion of sum of s squares error, this function is a convex function. In general, our cost function may not be convex, but not necessarily concave. You can see that the figure at the right side shows us a function which is neither convex nor concave. Okay, I will continue these concepts during the next videos. I highly recommend you not to miss the upcoming lectures because very valuable tips and concepts are waiting for you in the upcoming videos. and have a nice time.